try to get the AV guys' attention. Can you bring up my presentation? Okay, ready? Okay. Good morning, and welcome back to NASA's Asteroid Initiative Ideas Synthesis Workshop. We are coming to you live streaming on the internet as well as in person here at the Lunar Planetary Institute in Houston, Texas. I'm Andre Sylvester, Assistant Division Chief for the Software, Robotics, and Simulation Division, which is part of the Engineering Directorate here at Johnson Space Center. I'll be the leader of this Capture Systems session. As a reminder, those of you watching us today can join us virtually at www.nasa.gov/asteroid-workshop, all one word. There you can join the discussion using the chat feature on the session webpage or tweet us using the hashtag #CatchAsteroid. Again, all one word, #CatchAsteroid. Our moderator, Pedro Lopez, will be monitoring feeds throughout this morning's session, looking for questions you might have about today's program. So when we last met on September 30th, we had our NASA Associate Administrator, Robert Lightfoot, give an overview of the Asteroid Redirect mission and the Grand Challenge. In that overview, if I go to the next chart, please. In that overview, he described the three main segments of the overall mission: asteroid identification, the Asteroid Robotic Redirect mission, and the Asteroid Redirect Crewed mission. This morning's session will focus on one phase of the Asteroid Robotic Redirection mission, which is the capture of the asteroid element. You can see that on the little path timeline there, the red circle capture. So the purpose of this session is to explore the highest rated responses from the RFI. If we can go to the next chart. And this talks about some of the concepts that we've looked at here, and we're going to get a little more detailed briefing here in a few minutes. But you can see some of the reference system concepts we've been looking at. Next chart. Okay. So we're exploring the highest rated responses from the RFI related to the capture mechanism and identify the key topics discussed and provide NASA with findings relevant to initiative planning. So you can see here we had 4 factors that we evaluated each of the RFI submissions. We had 2 reviewers read each RFI, then we had a ranking factor, and then those that were ranked between with a 4 or a 5 in overall ranking were selected. We had 38 submissions. 10 of the 38 had an average rating between 4 and 5, and so that's what comprised the talks that we have today. If I go to the next chart. Okay, so again, I'm your session leader, Andre Sylvester. Each presenter is going to have 10 to 12 minutes for their charts, followed by 2 to 3 minutes for question or 2 from the audience, as well as those joining us virtually. After the presentations, there'll be an hour for group discussion in which you'll have a chance to ask more questions. We'll then take the last 5 minutes to recap today's session and go over the key topics discussed and identify findings relevant to assisting NASA in future planning activities. So to start the session, I've asked Brian Wilcox from the Jet Propulsion Laboratory, who is NASA's lead for the reference asteroid capture mechanism, to give us a little background on the requirements that drive the design, the challenges faced during the capture event, and how they arrived at their current concept. Hopefully this will help set the stage for our session. If you can switch to Mr. Wilcox's presentation, I'd appreciate it. Here you go, Brian.
Okay, thanks, Andre. Let's see, that 01 Wilcox. Oh, well, okay. Let's see, I think this is the September presentation. Can you go back to the menu and in 01, say where it says 01 Wilcox, that one. Well, we'll see if that's it. Okay, I wanted to talk to you, for those of you who were here last night or saw it on video, these are actually the same charts. I only had one set of charts approved for public release for this meeting, but I'm going to give enough, hopefully, different information that those of you who did see it last night will not be bored, and the people who didn't see it last night will not be confused. Okay, next chart. Oh, I'm going to drive. Okay. Basically, the spin state of the target is what dominates what the capture process has to deal with. And if the target were not spinning, I think most people would agree that this is not that challenging a task. But it's the spin and tumbling that is really the key issue. So anyway, this is a summary, and I'm going to just go through all these points, so we don't need to spend too much time on this. And let me apologize that this is in fact the September. These are the September charts. So if you were here last night, you saw the updated charts, but I'll do the best I can with the September charts. So the key issues are that the composition of the asteroid is quite uncertain. Of course, we do see lots of meteorites that are quite competent rocks. They're you not only have the stony meteorites, many of which are quite competent, but you have nickel-iron asteroids, which are extremely competent. But what a lot of people don't realize is that many meteorites, the C-types especially, the volatile-rich C-types, which would be of greatest interest for both science and resource purposes, those often have the consistency of a dirt clod or dried mud, and you can just crush them in your hand. So they really don't have very much competency, and they can easily break up. And then there are lots of reasons to believe that many of the objects, flying in space, have, are just particles bound together by molecular forces, van der Waals forces, that don't necessarily have a great deal of competence. And because the atmospheric process for meteorites selects those away, the population of meteorites does not reflect the population of objects in the in space, because the process of entry, descent, and landing on the surface of the Earth is a very difficult one for them, and so these very, very loose objects break up. And many of those, of course, if you look forward for resource utilization, the ones that are broken already into piles, those are the ones that are easiest to drive the gases off, the particles and so on, because there's so much surface area interior to the object. The other key issue is the spin state. Now, many of them are slow spinners, and many are spinning around a principal axis, but many are also tumbling. And for dynamical reasons, you would expect the time to relax to a principal axis spinner gets longer and longer for the smaller objects, and that leads us to believe that it's the objects, the relatively small objects the size of this room, which is what we're talking about here, are more likely to be tumbling than the larger objects. So the larger objects mostly have relaxed to a principal axis spin. And furthermore, the issue of how fast they are going. If again, the smaller objects, for dynamical reasons, we would expect them to be spinning faster. In fact, it's more, the distribution of surface velocities is more likely to be uniform than the distribution of spin rates. And if the surface velocity is the same for a small object as a large object, then the rotation period is much less. So here is a chart showing the absolute magnitude, which basically maps to diameter, and spin rate for those that have been measured, at least as of a year or so ago, I think. And the box represents the sort of 5 to 10 or 7 to 10 meter average diameters that we are interested for this mission. And you see, not that many have been measured, but enough to give you a sense of the population. And you see that there's only a few above about 1 RPM. And 1 RPM is where things start to get quite sporty. And so we're going to concentrate on that issue. And the idea that they are possibly dirt clods or even less competent than dirt clods, is a key issue. Again, I apologize for those of you who were here last night because this is an older representation. We are now looking at bags that are kind of like pie-shaped wedges that fill each of these, so that in the event, in the case of a high-speed rotator, you want to grab it really quickly, and in order to do that, we have we have cinch winches that are circumferential as well as axial that pull the rock down onto the surface of the front of the spacecraft for transport home after it's despun and tumbled. But in the case of a fast spinner, you want to get over it, and then you want to grab it quite rapidly. And so we have these interior bags that we can inflate, and of course in vacuum they will inflate very rapidly because there's no atmosphere pushing back on the front surface. So even a small amount of gas will push the bag into contact with the asteroid, and even at very small pressures, much less than 1 psi, you can get a lot of force distributed over many square meters of contact area. So again, last night I showed two versions of this, one for the fast rotators and one for the slow rotators. But in the case of the fast rotators, you would inflate those bags. If it's a slow rotator, and you know that well ahead of launch, you might not even have those bags in there. You would just gradually use the circumferential and axial cinch winches to collapse the bag over the object. The bag itself is crucial because it could be a rubble pile, it could be just a collection of loosely bound particles, and so we feel that we have to bag it completely, not only to just preserve all the material and not leak it all the way back to Earth, but also to protect our solar panels and optical surfaces and radiators and whatnot. Now here's an animation showing if you lined up the spacecraft on the angular momentum vector of the asteroid, then the instantaneous spin vector shown in the red there frequently is seen to just walk around the angular momentum vector in a cone, and that leads to a continuous rotation as seen from the spacecraft. Now here we have lined up the spacecraft on a future spin state of the asteroid, where at 30 seconds it will map exactly onto the instantaneous spin axis. So as the red axis approaches the line of sight, that's when there's no apparent motion, no motion at all for that brief instant. And so if you take that approach, that's the approach that we prefer for the faster spinners. And again, at 30 seconds, the relative motion between the spacecraft and the asteroid will stop, and that's the point at which you initiate the inflation of these airbags. And so right there, you trigger the airbags. They inflate literally in the blink of an eye, and now you go for a ride. Now you see that the spacecraft starts to accelerate promptly to follow the motion. There's almost no relative motion from that point. You want a fairly stiff system in order to achieve that, and we believe that with appropriate fabric shear panels within the airbags, we can get the stiffness we need. And the other nice thing is that the RCS thrusters on the spacecraft are not a large distance, and this is a typical simulation result, is that the RCS thrusters are far enough out from the belt line of the asteroid to give us a good lever arm with which to detumble and despin. And it only takes a relatively few newtons of force to despin this thing, detumble and despin it within a few hours. So amazingly, 1,000 tons spinning at 2 RPM, it actually doesn't take very much propellant to do that. So we've done a Monte Carlo simulation of about 5,500 cases with all these different conditions and every combination, where we've generalized the bag as a 6-DOF spring-loaded joint and then optimized all the spring damper characteristics according to limits set by our inflatables people who did, of course, the MER and Pathfinder airbags and are now doing the low-density aerodynamic decelerator. And it turns out that we can achieve, even at 2 RPM, well below the 1,765 Newton meters, which is kind of the baseline solar array deployment actuator torque that would break the solar arrays off the spacecraft, which is the main failure mode of this system. And so we stay below that, and we've also been told by those vendors that we could go higher than that without too much extra mass and cost. And with that, I'm done. Thanks very much.
All right, so now we're going to proceed into our list of presentations. I'd like to ask Daniel Shears from the University of Colorado to come forward. He'll be speaking to us today on asteroid research and modeling to improve understanding of small asteroid properties.
Okay, thank you, Andre, and thanks for the invitation to come out here. So what I'm talking about today is not so much a capture mechanism, but some of the research that we've been involved with over the last few years about the strength of asteroids, and I believe it's very relevant when we start talking about going through the capture procedure. So I'm just going to run through my slides on that. Here's really an overview of what we said in the white paper, and I'll cover this for a second, and then I'll talk a little bit more about the sort of strength that we can predict, in fact, and maybe even infer in the asteroid population, and what the implications of that could be. So the premise of the white paper is that it would be difficult or impossible to adequately design and develop methodologies for surface exploration, deflection, and capture without properly understanding their physical structure, surface covering, strength, and possible rubble pile nature, and stability to interactions with these bodies. And what we advocated for in the white paper was that continued research into the properties of small asteroids be funded in order to support all these other activities that are being discussed at this workshop. So there is a well-known relationship between the spin of asteroids and their sizes, all the way back to 2000 in the Pravik and Harris paper. And what we see is that, here's a picture of it. As we go to, I suppose we don't have a laser pointer. No. Oh, thanks. Okay. As we go to smaller and smaller asteroids, and Brian just showed this, they get faster and faster spin rates. Sort of a simple interpretation of this is that everything below this spin limit is rubble piles, everything above it would be monolithic rocks. And that's just because this line is roughly commensurate with how fast you'd have to spin a spherical body for cohesionless grains on the surface to spin off. If you dig into it, though, the real picture seems a little more complicated. When we look at asteroids, such as Itokawa and the radar shapes, it's clear that they're not just monolithic bodies. They're really assemblages of grains and boulders. There are some other things that I'll walk through, such as the existence of tumbling fast rotators, the computed mechanics of how asteroids fission, and the predicted physics of rubble pile asteroids. So what is a rubble pile? Fundamentally, it's not a bunch of equal-sized boulders, but it's the size distribution of boulders and grains that goes from microns up to potentially up to a couple hundreds of meters across. Measurements from Itokawa suggest it follows a 1 over d cubed size distribution, cumulative size distribution from millimeters to decameters, and from the sample, we know that the grains go all the way down to microns, and they were able to infer microns to millimeter 1 over d cubed distribution. For either of these distributions, the finest grains dominate in number and surface area over larger grains, but not in mass. But what it does imply is that larger boulders are either emplaced in or covered with, at some level, a matrix of finer grains. And what we've been looking at this are what the consequences of such a structure are. In fact, these fine grains can serve as a matrix that hold larger blocks in place, and if we just apply basic properties of cohesive grains measured on the Earth and Moon, we can actually give predictions for the cohesive strength of a rubble pile. So when we talk about strength of asteroids, there's two different things that we need to distinguish. First are chemical bonds, and these can be quite strong and sustain extremely high spin rates. And this is really the strength of a meteorite itself, whether it's a clod of dirt or an iron meteorite, something that's very strong. What we're really interested in are the van der Waals, or molecular forces, that can actually bind these these stronger blocks together with each other. And it turns out in microgravity, in particular asteroids less than 1 kilometer, these molecular attractions between gravel-sized grains can become as significant as their weight. And it turns out the amount of this cohesive strength needed to keep a fast-spinning rubble pile together turns out to be extremely small. So the way that we've been theorizing and modeling this is that these cohesive van der Waals particles between small grains can actually hold larger boulders in place. And we validated this with detailed granular mechanics simulations, and as I'll show in a second, we see evidence for this in the asteroid database. So here we just have 1 meter boulders with cohesive interstitial regolith van der Waals forces. We have centimeter-sized grains here, and we're just giving them the cohesive properties of lunar regolith, which we think is a reasonable analog. If it's cohesionless, if you pull these two guys apart equal to or just equal to their gravitational attraction, they separate and the grains stay in place. This would be a cohesionless rubble pile. But even for the regolith property of lunar regolith, when we pull these two guys together, if this regolith is cohesive, we see that we have to pull over twice as hard to get them apart, indicating strength. And when they do break, we see that the finest grains actually tend to stick to the larger boulders, which is predicted by theory. We can actually model this. I won't go through this equation, but the bottom line is, for reasonable assumptions, we find a strength of 25 to about 150 pascals. And that seems like nothing. In fact, it's like 0.003 psi. But this is strong enough to actually strengthen rubble pile asteroids. In this plot, I have shown all of the size rotation period asteroids. And here I've overlain the spin rate at which a rubble pile with a certain level of cohesive strength would actually fall apart. 3 kilopascals, it's about 1 psi. And actually there's not strong evidence that that regolith or rubble pile asteroids would have this much cohesion. But if we go down to our simulated cohesion of 25 pascals, what was reasonable based on our simulations, we find that we could still have many of the fast rotating asteroids actually be rubble piles still. Okay. So here's a very weak cohesion, and gives us an interpretation that maybe these guys in this range are also rubble pile bodies. There's additional evidence for this. Here I'm just plotting the binary asteroids, and we can correlate the cohesive strength between binaries and the size at which they trail off. And this is a statistically significant cutoff at the lower end of binary asteroid sizes. And we see it's actually consistent, not completely, but consistent with a weak cohesion of about 25 pascals. What this means, this is the spin rate at which we need to spin a rubble pile bodies to form a binary system. And if it's too strong, you have to spin it too fast so that when it breaks, the two components actually escape from each other. So we can use this to place a lower bound on the strength of these cohesion asteroids, cohesive rubble pile asteroids. Also, if we think through the physics of it, if we have a cohesive rubble pile and if it breaks, we would expect these to be fast rotating tumbling asteroids. And in fact, the best evidence we have for asteroid 2008 TC3 is that it was a rubble pile asteroid and it was tumbling, and we actually see that it lies along this 25 pascal strength limit, indicating that even something spinning at a few minutes can actually be a rubble pile still. So, and a final point, even if we have monolithic asteroids, It turns out that you have to spin them extremely fast, even to drive off millimeter or centimeter sized grains on the surface, just due to the cohesive forces. So even if we have a monolithic body, the cohesive forces between regolith means that they could still be covered in, definitely in very fine grained micron-sized dust and even up to millimeter-sized dust. So just to cover the summary and implications, small asteroids may be rubble piles or covered with fine regolith, and this has implications for asteroid capture or boulder sampling. What this means is a rubble pile asteroid may disaggregate under capture torques, and even if it is monolithic, there may still be a fine regolith covering that could pose a substantial dust contamination and abrasion issues for either an asteroid capture or boulder extraction. This possibility is consistent with our basic understanding of physics, granular mechanics, and asteroid properties. So in summary, tumbling asteroids also may have resulted from a rubble pile fracture. Bodies spinning slower than the weak strength limit may still be rubble pile bodies, and any monolithic asteroid or surface boulder will, and most likely will, still have a covering of fine regolith and dust independent of spin rate. So those are the points I wanted to cover. Thanks.
Okay, we have time for some questions. If you have a question, please come to the microphone. Does anyone in the room have a question for Mr. Shears?
Just wondering, as you were describing that, is there any possibility of a contribution of electrostatic forces in this type of, do we know anything about the properties of conduction versus dielectric? Could there be some kind of...
Yeah, there certainly is a possibility of electrostatics. Electrostatics, though, will essentially vary over time, where these molecular forces are sort of consistent like gravity. They're always there. If you go there, though, and if you, rub two rocks together, you'll probably generate a static field. We believe that there's plasma fields on the surfaces that could also influence what happens to the finer grained dust once it gets liberated from the surface. But that's a very interesting topic, but yeah, not one I'm covering here.
Are there any additional questions in the room? Thank you, sir.
All right, thanks.
I think our next presenter will be virtual, and so are we bringing them up in the back here? Yeah, we're bringing them. Okay, great.
He's up. Can you ask me?
All right. Mr. Mum, are you online?
Yes, I am.
Okay, let me give you an introduction. Our next speaker is Eric Mum from Honeybee Robotics, and he'll be discussing an anchoring system and lasso snare capture system. And Eric, I'll give you a time check at 10 minutes.
Okay, thanks. I appreciate it. Good morning, everybody. I'm sorry I couldn't be there in person. We actually are presenting multiple sessions, so I have a generalized slide deck here. Not all of these are pertinent to the capture discussion, so I'll breeze through the early part of this. So I just moved my slide deck to slide 2. I want to make sure that the Adobe Connect is working correctly.
We see slide 2.
Okay, great, thanks. So for those who aren't familiar with Honeybee Robotics, we're a small spacecraft mechanisms company. We've contributed multiple mechanisms, most notably to the Mars program. So we've been on Mars exploration rovers, where we contributed rock abrasion tools, which are featured in this chart here. We had hardware on Mars Phoenix lander and 2 instruments on subsystems on Mars Science Lab's Curiosity rover. Next slide. So here you see the slide deck actually covers on 4 topics, and like I said, I'll breeze through most of these. In our RFI response, we covered multiple technologies that the Honeybee is in development or has developed. In sort of a flyby scenario or a mapping scenario, we have developed some laser-induced breakdown spectroscopy systems whereby you could do some remote sensing, a miniature 3D scanning LiDAR system that could be used to map an asteroid. We have developed concepts through multiple mission proposals, most notably in the Discovery program, where we have designed an impactor that could be used to understand physical properties of an asteroid by impacting it. Honeybee's forte coming up through the Mars program is really on sampling and supporting the science of robotic missions. Through that development work, one of the sampling instruments that we've developed is what we call a touch-and-go surface sampler, whereby, again, sort of on a standoff position, you could lower a tethered surface sampler to perhaps do some in situ science or pick up some of this loose rubble and pull it back to the spacecraft for subsequent analysis via some onboard instruments. We've developed harpoon samplers where you essentially fire ballistically a harpoon at an asteroid and you sample it, and it's tethered, so you reel it back to the spacecraft again, so you could do some science in situ. And we've probably developed more planetary drills than we'd like to admit. But we have developed robotic drilling systems for the Moon, for Mars, and for asteroids. We've got tens of designs ranging from sub-kilogram, sub-centimeter drill systems all the way up to deep drilling systems, 10 meters and beyond. And so this is, again, another method for performing some in situ science, for collecting a sample from the asteroid and characterizing it. And then we've also developed some pretty novel pneumatic sampling systems. So this could be used for very low impact systems where you essentially use pressurized gas in a way similar to what Brian was alluding to earlier in this morning's discussion. And it actually takes very, very little gas to acquire a good amount of sample, loose sample. This was designed for Constellation program originally to sample on the Moon, but it can be applied in this scenario as well, where we could tether something down to the surface and via pneumatic excavation technique acquire a sample using very little impact to the asteroid. Okay, so most pertinent to this session here, finally, there are a couple of concepts that we contributed to the RFI. The first one is, I would say, similar to some of the capture techniques, or the capture technique that Brian mentioned, obviously on a much lower, smaller scale here. We developed what we call our lasso system, where we, and this was developed as a concept for docking to satellites spacecrafts that weren't designed to be serviced and weren't designed to be docked to. And essentially, the way this system works is if you move from number 1 in the top left here, where we're at a standoff distance from, in this case, from a spacecraft, you can see a representation of the Apogee kick engine nozzle there in the bottom of the screen, or in the bottom of the image. Where we're at a standoff distance, and between 1 and moving to the top right, number 2, our snare system is deployed, and it's deployed in this demonstration via a series of carpenter tapes. But we envision a little higher stiffness system in future development using some graphite roll-up beam assemblies that we've worked with a partner of ours on for deploying large solar arrays. But you know, the stowed to deployed ratio of a system like this could be very large. So the standoff distance could be quite large. And at the concept surrounding our docking system, or in this case, applying it to an asteroid capture, would be to influence the target minimally prior to soft dock. And so effectively how this system works is that you deploy the ring, you deploy the snare around your target without touching it. So there's zero impact prior to the in position ready to snare or capture it. So that's the position that's represented by block 2 in the upper right corner here. And then in block 3 you can see in the graphical representation in the upper right corner of each block is the configuration of the snare. So this is a spring energized snare that's driven by a winch. And so once the capture ring is in place and the snare surrounds the target, then the winch closes and constricts from a dilated state to a constricted state around the target. Again, in this case, it's an Apogee kick engine nozzle. And then once it's constricted, once it's captured the target, in image 4 there on the bottom right, the deployment mechanism, or deployment retraction mechanism, retracts it and docks it to the spacecraft. So our initial thought here was that, you know, the system as is, at the size that it's represented in this demonstration, could be used to pick small boulders off of a sort of a larger asteroid or a larger collection, larger rubble pile. In the event that you'd want to, you know, sample a subset of the asteroid. Once the boulder is captured and brought back to the spacecraft, you could even, once it's hard docked, you could even perform some drilling, some robotic contact science or robotic drilling and sample acquisition aboard the spacecraft as well, if we wanted to do something like that. And as far as, you know, scaling this system up, this obviously, you know, there's no bag around the deployment system, and so that would have to be added. But there's no reason to believe that something like this couldn't be scaled up to a much larger size. And it's, you know, it's a similar concept to what Brian had presented earlier this morning. And so this is our LASSO concept. Again, it was initially designed for spacecraft docking, and we feel like it could be modified and applied to either pulling small boulders off of a rubble pile or off of a larger asteroid, or even scaling up to much larger system and capturing the entire asteroid. So our group out in, for those not familiar with Honeybee, we have a group out in Pasadena, California, who works a lot with JPL and has developed, you know, these many drills that I alluded to earlier.
Hey, Eric, this is Andre. You got 1.5 minutes left.
Okay, thanks. So that same group has also developed, you know, a drilling system or a landing system, a very low impact landing system, whereby you could apply thrusters to hold the spacecraft down on the asteroid, and deploy this anchoring system, which can work in a variety of competencies of rock. So it could be applied in very loose rubble, or even higher competency, you know, limestone-like ultimate compressive strength, so that you could actually anchor a body to an asteroid and then perform some surface science there. I'm almost finished here. And then this is a concept that we came up with that's, of course, again, very similar to the concept that Brian alluded to or presented earlier this morning. Not too much to explain here. I think it's pretty self-explanatory. I believe that, since I'm running out of time, I believe that completes our capture mechanism portion of our slide deck. So with that, I'll leave it at that.
Very good. So Eric, I'm going to offer to the room, is there anyone who'd like to send a question to Eric? If you do, please step up to the microphone. Okay. Yes, sir. Go ahead to the microphone, please.
Are these systems quick enough or agile enough that if you're trying to pull a boulder off a larger object that's tumbling, that it could do it before the target tumbles out of reach of the lasso system?
The lasso system right now, I wouldn't characterize as being extremely agile. However, I guess that's a trade that we would need to make once we define some requirements a little bit better. I think some of the numbers that Brian presented earlier, we can go back and take a look at whether or not we can support the kind of tumbling rates that we might expect. But I will say that the system right now is not optimized for and wasn't designed for being extremely agile. So there's no reason to believe that we couldn't make it more agile. Whether or not it meets ultimately the requirements to pull a boulder off an asteroid, I guess, would be to be determined.
Very good. Are there any other questions from the room? All right, and we don't have any online yet. So thank you very much, Eric. Let's give him a hand. And Eric, if you have time, continue just listening in, and we'll have a wrap up at the end of the session.
Will do. Thank you.
All right, very good. All right, we're going to move back to in-room presentation, and we have Kenneth Steele from ATK Space Systems. He'll be talking about two concepts for deploying capture bag using integral ribs or expanding hoops and telescoping booms.
Thank you, Andre, and welcome.
There's a laser pointer now on the stand.
Thank you. So I'd just like to share a little bit about ATK as a premise. Beforehand, give you a little bit about our heritage, and I'll talk about some of the concepts that we've came up with. So we've been in business about 35 years of a lot of products that have heritage on the space station, including the booms that deploy all those solar arrays out there. We worked with Lockheed on those. We've done synthetic aperture stable structures. We have worked with JPL and NASA on a variety of products. And the one shown in the lower left there is the NuStar, where we developed the 10-meter boom along with both the optics and the X-ray payload elements, and integrated those, and then built the solar array also for that. And then recently, you've seen the pictures for Megaflex, and we were also developing that as part of the Game Changing Technology Office, now TDM office. And so we've got some great pictures in here for you. Just a little bit not related, but somewhat related. Pretty exciting stuff. Let's see, what do I got here? So our heritage products include solar arrays. We have flown over 100 wings in orbit. We have a variety of mechanical boom systems. We have flexible arrays that have flown on Mars. That's the Mars Phoenix lander. We also did the deployable boom for that camera. On the right there shows our Ultraflex arrays. First ship sets being delivered to Orbital for their CRS platform. So the Ultraflex is a real live product. We've done a variety of extended, enabling multiple shuttle missions. This is the boom that was done on the shuttle. We've done SRTM on the shuttle with a 30-meter boom, so that's over 100 feet long, with a 400-kilogram payload. So we know how to build structures that are stable, strong, and ability to both deploy and retract. I think the biggest point that after 35 years of on-orbit products, we've never had a failure, and I think that's key to our heritage and capability. From a relevant experience standpoint, we've got a variety of programs that I'll talk about. These include for X-32, this was a program that we worked with one of our customers. It was a multi-layer tensioned sun shield, and 10 meter by 10 meter figure, looking at a pop-up tent that you have, you take to your soccer game when you're watching your kids. Only those are all integrated together, and they deploy up in a synchronized fashion with a multi-layer fabric on top of that. And then we've stowed that and deployed that and developed ways how to keep that from snagging, keep it from tacking or bundling up and then sticking and ripping. Well, we did this, one of the initial solar sail deployments, and that's a picture of the top view of Plumbrook. So this was 20 meter by 20 meter, about 100 feet across, if you look at the diagonal, and deployed that in vacuum and at both the temperature extremes and showed how that would operate there. We are developing Megaflex. Here's a picture of our EDU wing that's basically going to Plumbrook next month. We'll be deploying that in vacuum, and that is 30 meters, I'm sorry, that's 10 meters in diameter. We'll produce about 20 kilowatts per wing and extensible up to a 30 meter diameter, which would create power of about 175 kilowatts. So we're very excited about that, and as you can see, just the size of that and how that's come together is on the relative scale of what we're talking about in terms of total size. We've also developed a sunshade for a large membrane optic telescope that kind of bodes well to our experience in this type of products here that deploy and then with mesh or other types of materials with it. So at ATK, we've got a lot of innovative guys, and when we see something like this, we kind of get in a room and do some brainstorming. And these were the top three that we felt that were worthwhile of doing kind of a trade or a grading scale on. I'll talk about each of those in more detail, but I just wanted to give you a top view of where we came up with. The criteria that we've worked with is something that we've found that is pretty applicable to both our commercial customers, our NASA customers, and most of our products we have to deal with is that, well, this is new, compatible with an odd-shaped target. We have not done this before. But looking at low mass is always a key element because we have to launch this thing. Low stored volume is always a key element, and this is for the total system, not just the elements in it, but actually the stowage of it, the deployment of it, and how that is mechanized on the spacecraft. The simple mechanization, how do you release this, and is it with a lot of motors, or is it a simple strain energy spring-loaded device that comes out in a synchronized fashion? We've done more of the latter than the prior, again, so deploying things out with springs in an articulated manner or driven out with a simple drive motor. Verification and validation is one of the key criteria that most of our customers want to look at when they consider a new technology or something with a lower TRL. How do we get confidence that this will work in space? And most of our products have that capability, and so we saw that as a key criteria. Looking at heritage and maturity, we wanted to take high TRL items, at least a 6 item, and a lot of these have TRL of 9 elements of those that we're looking at, so we felt that that was a key element also, and as I talked earlier about stowed launching. So our first concept was a wrapped rib design. I'll talk a little bit more about that, but it's more of a conical ribbed element that has a mesh body around it, and that this is fed out, and I'll talk about that a little later, but basically comes and grabs the asteroid and then cinches up around it and then brings it close to the body. The expanding hoops looks very similar to what Brian presented. The primary difference is instead of inflatable tubes, we've used articulating booms that have very high strength, able to both deploy and retract. They have, and again, we use 6 of these, 3 that come out radially, and then 3 that would come along axially with a kind of a scissors hoop around both the top and bottom, and then a lanyard deployed bag that would sit in front of that. Our concept in here was that lanyard would then collapse or be pulled closer to that bag to bring the asteroid into a location closer to the satellite. We looked at inflatables, and I'll admit, we don't have a whole lot of experience with inflatables. In our trades with them, when we started talking with some of the manufacturers in those systems, trying to integrate into ours, we found that some of the strength, at least for the past missions that we've flown, the strength of a deployed boom didn't really compare well with what our articulated booms would be able to do. And then the canister fill stations, a lot of that mass that, from an overall performance and packaging standpoint, a trade that didn't always bode well for us. Again, I don't want to offend anybody. I think there's a great place for inflatables, but in our past experience with our customers, we haven't found that right mix. So I'm going to go a little bit more detail of each of these. And, the favorite concept is the first one. Again, I don't want to offend anybody about inflatables, but as I spoke, that the difficulty about inflatables is the strength of them and the sustained strength. This is not a deployment where you, like a bag. The bag systems work great on Mars, and they've worked in a lot of different places where you have a bag that expands. It allows us to impact a surface without, with a cushion, but it doesn't, for this application, we didn't see it as a benefit. We looked at the expanding hoops, which I talked about that, the hoop bag that comes along and expands out, grabs around the asteroid, and then pulls that together, was a complex we found as a viable approach. There was some increased mass complexity compared to the wrapped rib approach, and not as compact as stowage. So a wrapped rib really came from concepts we've already seen out there, the wrapped rib antenna that developed by Lockheed many years ago, and only we wanted to pull it up more like a hoop skirt, so give a little more depth to it, and then inflate the bag like a Jiffy Pop. And most of you are my age, so you understand what a Jiffy Pop bag is, rather than just the paper bag that goes in the microwave. But those are kind of the schemes we look at in terms of how to stow and deploy things. So this is a wrapped reel device. Again, would wrap up these reels. This wrap would be rolled up upon stowage, and then tractor fed out, and then retained with a lanyard on top, so that as it fed out, it wouldn't just go radially out, but would radial want to pull up, and then because of its own strain energy or its spring force itself would want to come into more of a basket or a hoop like that. The concepts of feeding this out are a tractor feed, something that would give positive engagement for both deploying and retracting from the concept there. So the top view here, the ribs would be in there, the bag would be folded over it, similar to the Jiffy Pop, and stowed in, on top of the launcher in a similar fashion that we show here. Step 2 would be to unfurl this. The bag would be retained by the ribs, and as we move up further, we looked at a 20 meter, and the reason I mentioned the 20 meters is because we did some mass estimates on this and it's part of our trade. I'll go quickly. We target approaches, we capture the bag, and then we cinch it, like many other cinches on shoes and gloves, that we tighten this thing up like a straight jacket, and then pull it in again with these retractable ribs, pull it close, and bring it back engaged with the spacecraft. Now, there's a lot of things of talking about is how do we despin this, and I think that was covered by a lot more studies. We were just looking at the bag, so whether this has to be on a long tether and reeled back in because of its spin rate, or as Brian showed that, hey, if we get in motion, we can get this dialed in. I think they're all feasible approaches. We looked at bag construction. We've got experience with Kevlar and Vectran, which are very strong elements. Again, for this application, you've got some UV radiation stability you need to look into. We also talked about maybe including some flaps or doors in certain locations that would allow easy access, and then even folding it back up to the specific asteroid that we grabbed. Did some weight estimates. So the wrapped rib came at about 214. The expanding hoops came in about 270. So again, just kind of looking at the primary driver here was the ribs versus the telescoping booms as a more of a mass-saving approach, and stowing volume. So summary, we favor an elastic structural member that's mechanized for deployable and retraction. We think an articulated structure that has some strength to it, based on our extensive flight history, is a real benefit to this. The wrap rib approach we feel is a very mechanically simple approach. Simplicity is always left to the details, but when you look at a simple approach, it has a much more viable chance of operating in space with less complications. We feel we can readily mock this up and do some development deployments and demonstrations. We really don't look at this as new technology is needed. We don't see this as a stretch, and a lot of existing materials and potential processes could be used. So we feel that we are well suited to work with NASA. We don't think that this is the end all. There may be a hybrid system using bags on the internal, a truss structure or the wrap rib on the outside, and that's really what we do well also is work collaboratively with both our customers and partners to come up with the optimum solution. So that's all I have to share today.
Okay, do we have any questions from the floor? If you do, please step forward to the microphone.
So have you, one of the things that I would say,
Get a little
closer to
closer. Thanks.
Okay, thanks. One of the things that I would say that on the NASA side, when we've looked at the various things and multiple concepts, is the dynamics of the D-spin is the big thing that you have to deal with. There's been several iterations on the NASA side. One of them kind of looked at some things like this, and it was always while I understand your point about inflatables and can you really do the ground testing you need to do, the dynamics of the D-spin and making sure you understand how that is going to work is probably the biggest thing. I didn't see that much in what you guys have done to date on that.
And again, we were really looking at the capture bag, and so you're right, we didn't look at the D-spin, and some of the work that Brian did was very enlightening, and so that's where that may be, we know we're not a one-stop shop, but we're a good collaborator, and so I think the system could go well with another bag system or other type of D-spin system that could grab onto that rock without tearing the bag.
Next question.
Do you have any comments on how applicable your approaches are for a boulder collection rather than capturing an entire small one?
Well, that's why we went with a bag that would allow us to completely surround the particular element in question, the asteroid, and so that as you bag it and cinch it in, you're not taking a point, but really just an overall bag approach that whatever's in there stays in the bag, even dust.
Right,
So-
but in terms of interacting on the surface of a larger asteroid and making surface contact, have you looked at that at all?
No, we didn't look at that. Primarily just capturing it is that we looked at.
Okay, thanks.
All right, let's give our presenter a hand. Our next presenter is Scott Belbin from NASA Langley Research Center. He'll be discussing extendable retractable boom capture system.
All right, thank you, Andre. So I worked with Brian Wilcox and Andre on the analysis of the alternatives to the reference concept, and so I got real familiar with the JPL concept, and I want to really extend our appreciation to Brian and all the work he's done. It's an incredible amount of work that JPL has put into this, and they've come quite a long way on it. So as I was working through it, some of the key points that came out were how difficult this is going to be. So we're talking about possibly a rubble pile, as Brian has talked about this morning. It's got to fit in the payload of the fairing. So we're looking for something that obviously we can launch. It's going to be capable of up to 1,000 metric tons, and then we've got to accommodate the different asteroid shapes as we've talked about already today. We're dealing with a very short time to launch, 2018. So looking for a high TRL approach is always a great way to go. So I was looking for something that we could deploy, close, and retract the bags without robot arms, and then leverage the available electrical energy on board instead of carrying another energy system like a gas system. So we also needed to be able to reliably model the system. So rigid structures are readily modeled and simulated. They're also rigid structures enhance the dynamic stability. One of the things that we looked at early on when we saw the JPL concept was we were worried about the dynamics of spinning this up to 2 RPM. It's a massive bag. It's 15 meters in diameter, And imagine a big inflatable trying to rotate and get out of balance. How do you keep that balance? So I thought about what can we do to enhance that dynamic stability. So I looked for rigid elements. So this is going to look real familiar. This looks a lot like what ATK just showed. So here we've got a picture of in the stowed configuration, very compact. Uses deployable booms to extend the bag out, and it's a single ply Vectran type bag. Easy to get through, easy to put access panels into for the crew access. And the kicker here is to be able to conform to the shape, use the cinch lines, and allow the booms to actually bend and conform to it. We don't need to keep the booms in their extended configuration in their pristine shape. Allow them to conform to the boulder as it contracts. We put together an animation. It didn't run so good in the program or in the slide set, so I did some screenshots. There's 6 actuators. They're real type deployable booms similar to Northrop Grumman stem booms, which work similar to a tape measure. When you pull a tape measure out, it goes from a coil configuration out to a rigid shape because of the cross-section changes as it comes out. So as these extend out, it would pull the bag up and out. And I've got some details on that. So again, it deploys a single ply Vectran bag. Again, circumferential cinch cable similar to the JPL concept. And the booms can retract to draw the asteroid up against the spacecraft to rigidize the asteroid to the spacecraft for control. And then independent boom drives allow for some amount of CG adjustment. Once we grab onto it and the cinch lines collapse, collapse the booms around the asteroid, we can then pull one side in or let one side out. They all drive independently. We did, just as a sanity check, we did some preliminary calculations and came up with some shapes. I favor the lenticular shape because of the kinking ability, the way it can collapse to get around those shapes without losing any structural integrity. We can still pull on it, and it retains its tensile capability for coming back to and reeling back in. And if we get a kink that has to go into the reel, that can happen. That kink won't keep it from going back into the reel. We did a quick mass estimate on it with some of the CAD work we did. Total boom mass system, we're at 124 kilograms. And adding in the bag, again, it's a lighter bag. It's a single ply Vectran bag versus something that's inflatable with multiplies. Attachments, cabling, et cetera, et cetera. And then adding in 30% contingency, we're at about 365 kilograms. For the RFI, I put together a schedule. Basically, if we were kicking off at the beginning of this fiscal year, which obviously we're not, and trying to get up to a 2018 launch, we would have to do a concurrent design and development testing program. This would include, the schedule includes time for boom tooling design. These are, if we're going with composite booms, that would take special tooling. These are long. These are on the order of 18 meters long. So we would need to have tooling that that can heat the composite without having to go into autoclave. So it would be tooling, special tooling. So we've accommodated for that in the schedule. It also incorporates a ground test article build and test program. Potential next steps would be boom cross-section design and analysis, section property demonstration, boom-to-drive buckling limit demonstration. That's where the boom deploys from the reel mechanism. That's going to be a hot spot in bending. So we'd have to have some amount of compliant members at that point to either by having thicker wall sections in the booms or having some compliant members in the drive. Bag material demonstrations and puncture resistant tests, et cetera, et cetera. Going a little fast here. So anyway, I think we've come up with something that's dynamically stable and spin up, and that's the big point. Is when we first looked at this, like I said, we were really worried about how we can control an inflatable bag of this size at up to 2 RPM spin. I believe it's going to be a little difficult to keep that stable. We're looking at medium to high TRL on technologies. These are drive systems that already exist and have been used for many, many years in deploying solar arrays, just as the ATK gentleman has said. We're using the electrical system and not a gas system, so we're not carrying the extra mass of a gas system. We can demonstrate in 1G environment, similar to what Brian has said with their concept. You'd put it in a actually vertical configuration, and because we're not in a vacuum, because we're not inflating, we don't necessarily need to be in a vacuum chamber, just still air. We could actually do this in a closed hangar if we had to. And we believe we've got improved crew access with this, since we're only going through 1 ply. It's easier to cut through, and with all the inflatables collapsed down with the inner bags, that's a lot of material to cut through for the crew. So we think we've got better crew access in that because of the 1 ply. That's all I had. So any questions?
Okay. I think we have a question from online. Did you, could you
Okay, so we have a generic question. Basically, it says that the presenters are talking about matching and then slowing angular momentum. Have they considered the physics observed on a merry-go-round, deploying large arms to slow the spin rate, retracting them to increase, and putting propulsion systems on the arms to adjust spin as necessary at maximum efficiency based upon distance from the spin center? And I'm guessing this question would be basically addressed to the general audience, if someone could address it.
Scott, you can take a run at it.
Okay, I think I understand what you're talking about. You're actually talking about putting something onto the asteroid as a separate system of reacting the forces. Actually, we covered some of that in the analysis of alternatives, and one of the things that we hit pretty quickly is now you have a separable spacecraft, and all the implications that go along with that are additional development costs, additional control and guidance on separable spacecraft. You have something that has to go and independently attach to the asteroid and then be commanded either by the mothership or be independent. As that starts to turn, you go into a blind spot, so you get out of communication range. You have no line of sight between the mother spacecraft and the far side of the asteroid that you're trying to detumble. So we do consider it, at least from the analysis of alternatives, and saw that it was probably going to be a program buster.
All right. Any questions from the floor?
So I'll ask the same question I did before. How much simulation have you done on the actual D-spin process for this?
I have not. This has been, I've been saying, this has actually been work that I've been doing by myself, basically spare time. So it comes with the same problems that any of these have with any of the spinners, and it's the ride 'em cowboy. Yeah. Unless we can, get the asteroid in and detumble it while the spacecraft is, stationary, we're all going to face the same issue with doing this.
I mean, usually you make these booms out of some kind of composite material, and when you do that, you get to a certain point, and all the little booms are going to snap if you get to a certain load point.
Sure.
Torsionally,
right.
Especially.
So
when this thing
you're right,
wrap around itself.
And so the calculation I showed up here was looking at that. That was the first order calculation that we performed, and that was looking at the worst spinner, the highest mass for that worst spinner, collapsing in, and then taking that torque, applying it at the base of the booms to the spacecraft, and seeing if we busted or not.
With these flexible structures, I mean, it really requires a fairly detailed 6DOF analysis that goes through, and even in a Monte Carlo sense, goes through the various scenarios that can happen in order to understand what the loads really are on these things, because you could have point loads that go way beyond what you're talking about.
Absolutely, absolutely. And I think it's important to emphasize that what we're trying to do is extremely tough. It sounds simple, go grab something floating in space, but as soon as you put the spin on, just like Brian has said, you know, it becomes a difficult problem, and it's going to take quite a bit of engineering to get it done. But I mean, I think we've got a great group of people who have fantastic ideas, and if we can pull those together, I think we'll figure it out.
Another question from the floor? All right, oh, yes, sir, go ahead.
As far as the de-spinning goes, would it be possible for to build in a joint between the bag and the spacecraft that would allow it to rotate, to take the stress off the bag and the assembly of the capture itself, and put it down to a point where you can essentially break the spinning?
Sure. We actually talked about that again in the analysis of alternatives. That's one of the ideas that came up. Putting a gimbal of some sort between the bag mechanism and the spacecraft. And that works great for single axis rotation, but as soon as you get the second and tertiary axes going, then you get into a point where your spacecraft is going around and you run out of gimbal range. You can't, you just can't do it on the second and third axes. And Brian's dynamic animation, if you saw that, is a great demonstrator for that.
All right, well, thank you for the questions, and thank you, Scott.
Okay, thanks.
Okay, we've got our next presentation is Paul Fulford from MDA Canada, and he's going to discuss the use of underactuated linkages for robotic grasping of asteroid.
Okay, thank you. I'll start off first with just a really quick overview of MDA. MDA used to be Spar Aerospace in the 80s, 90s, and early 2000s. And our history of capturing either cooperative or uncooperative objects in space started back in the 80s with the Shuttle Remote Manipulator System, doing work capturing and repair of the Hubble Space Telescope, adding extensions and different features to our robot manipulators to survey the underbelly of the space shuttle. And then moving on, we're currently supporting free flyer capture of the Dragon capsule and HTB, and the Canadian Space Agency over the last 3 years has invested a significant amount in the development of a next generation Canadarm, so the third type of Canadarm. And MDA as a corporation has also been looking at satellite servicing, and we're really treating this problem like any other capture and operation of a spacecraft or an uncooperative object. So I'd like to start off and introduce you to Sarah. So Sarah is an end effector hand that was, the basis of it was developed by the University of Laval in Quebec, and it's a self-adaptive robotic auxiliary hand. And MDA has collaborated with Laval mainly for the purpose of developing multi-purpose type end effector actuation that can grab onto any type of surfaces. So MDA has a license to further develop this technology. When this problem came forward, we had a group of engineers, and we had a few brainstorming sessions, and this was sort of unanimous as to a good way to go. This might be a good point to highlight a few assumptions. Some of the assumptions are that whatever will be grabbed, we assumed would be consolidated. So be it extracting one from a regolith or a rubble pile, or just a free-flying object. That is the main premise for this. So what is under actuation? It's the title of the presentation. So under actuation means a number of things. One, the self-adaptive portion is the manipulator fingers adapt to whatever surface it is that they're grasping. And it's only driven by 1 degree of freedom per finger. In fact, this hand it has 3 fingers it has 9 degrees of freedom and it only has 2 actuators, one to reorient the fingers and one actuator to actually pull them all down at the same time. So you could even reduce it further. So it's based on using 4-bar linkages and unique triangular features. Let me see if I can. So triangular kinematics, where the 4-bar linkages from an actuator at the base permits these appendages or fingers to conform over the shape of the body. So an under-actuated linkage concept, the initial configurations held open, passively sprung-loaded fingers held open. It can also be active. Just to give you an idea of the size that everyone's talking about, we just tried to put this graphic together to show that it's similar to things that we're used to seeing all the time. So just think of that flatbed truck going down the road with a great big rock. Each finger would be approximately that size. So the final configuration of the number of fingers, it could be between 3 and 5, would conform to the shape of the asteroid. And in that view, you could actually, there's 2 EVA crew member walking up and along the truss members. I think at this point in time, being that I'm a Canadian, it's my birthright to draw parallels to hockey. And we couldn't do that here. It's a little too complicated, but it does look like the Toronto Raptors' claw grabbing a basketball. So that's our Canadian draw. So this is just a final view with Orion and the ARV with the crew out on top of the asteroid. So we did do a reasonable amount of work. We've done hand calcs. We looked at detumbling rates and deployment of thrusters and whatnot on the appendages. We took it as far as could we stow this device. So there's a CAD model up in the upper right-hand corner that we proved to ourselves anyway that we could get it into a nice stowed configuration. And some of the other benefits is that through all phases of the operation, including post-capture, it permits observation of the target. So all the way from rendezvous to proximity operations, you can see exactly what you're going after. And then once it's captured and for the years to follow while it's grabbed, both for transport through to science, you can actually see what it is that you have in hand, so to speak. It does reduce the risk of snagging, abrasion, and uncontrolled motion. And we did do some preliminary mass calcs, and I was comforted to see some of the mass calculations here today. We're in and around the 400 kilogram range. And that concludes my presentation. Thanks.
Do we have any questions from the floor? Yes, sir.
I noticed that you're grabbing it with a hand, so that suggests to me that if, for example, you picked up a boulder and then it was decided that another boulder or another asteroid was to be picked up, perhaps it's a binary or something that you've reached, and the other one in the binary pair was more interesting. Could you let go of the one that you picked up and go get the other?
Yes, you could.
Okay,
yep.
Thanks.
I was interested what the pressure of the claws or grappling arms are on the object itself, especially if you go through a D-spin.
I don't have that at hand. We did look at it. We looked at a number of different D-spin or detumble scenarios, and it was believed that the grip force is sufficient. For robotic applications, we're looking at using EVA handrails to hold on to while we manipulate systems that are rather heavy and have huge inertia. So,
I guess my question is motivated from the other side, which is how strong is the object, so that you might just crush it or crumple it or break it apart if it's like a clod of dirt or something like that.
It would be a function of the base actuator primarily. I can't tell you exactly what kind of minimum forces we could apply.
Yeah, we do have an online question I'd like to address, and then we'll take another one for the floor. Online question?
Okay, and the question was submitted by Ustreamer939. Have you considered designing the system with the fingers being able to be shifted, such that if one is damaged, they can turn it into a 4-finger system?
So I'll just go back to this device here. So if you look carefully at this component, there's 2 fingers this way and 1 finger this way. And then if you look at that view, they're all evenly spaced in a circumference. So in this view, when I said that there's only 2 degrees of freedom or 2 actuated mechanisms in this, one is to reorient the fingers and one is to pull them down. So I think the answer to that is yes, we could also have that degree of freedom if required.
Okay, now a question from the floor.
The rock is heated by the sun as it approaches, driving off volatiles. Could you shield it with airbags having reflective surfaces? Put airbags on the side of each of the fingers to shield it. Also, that keeps the dust in.
That's an interesting question. This device actually has different types of pads that have been explored in terms of how things could be gripped. So those fingers could also have other types of surface materials. One of the bullets that I removed just on the plane coming here was the combination of this with a deployable bag. It just seems a little too complicated to me, but perhaps that's something as a workshop that we could talk about. So maybe combining an inflatable bag, having different material properties, and I've lost the word, but the tactile properties could certainly be explored. I think it's all possible.
Yeah, I think maybe you had the same question as I did in terms of could you have, in essence, a glove over the hand so that, and maybe those sections could be peeled away for access.
Sort of like a baseball glove.
Like a baseball glove, but you know, the problem is having flexible materials that contract and expand, or coming up with a clever way of having those materials fold and still providing access to the material underneath.
I think that we can. The only place that I take pause is in the upper corner for the stowed volume and how to get all that material and those robotic fingers stowed properly.
Yeah, sorry, just stay up here. You know the pop-up tents that you have for like hanging out at athletic events so you don't get covered with sun. They have a whole folding, approach
Scheme.
Exactly the same way that could be employed if we can get the right materials.
Yeah, I agree.
If dust and debris is a concern.
I agree.
Any more questions from the floor? Anything more online, Pedro? All right, let's give our presenter a hand. So we're running ahead of schedule, so I'd like to propose a 4-minute break. We'll get back together again just before 9:30, so if you want to take a little stretch, please do. And our next presenter is Carlos Enriquez from Boeing, who will be discussing assessment of alternative capture system concepts.
Good morning, ladies and gentlemen. My name is Carlos Enriquez, and I'm representing the Boeing Company today. I'm honored to have received the invitation by NASA to participate and present at the Asteroid Workshop. I have the pleasure to provide to you a brief summary of the studies we performed to evaluate concepts for the asteroid capture missions to share with NASA and guests in this workshop. The study we performed on the subject of asteroid capture indicates that flight-proven systems and key technologies can be integrated to achieve an asteroid capture mission. For this study, Boeing leveraged its International Space Station experience of assembly of large structures in space, as well as expertise in several types of attachment mechanisms suited for each task. We used dynamics and control simulations extensively to ensure that the space station assembly on orbit, and because we could never test the assembly on the ground. The space station assembly has truly allowed us to master working in space. If we choose a mission to an asteroid with a mass of 1 million pounds, this is equivalent in mass to the International Space Station, and it is well within the capability of propulsion and guidance systems to control it and to or redirect it. To meet this challenge, the Boeing Company and the Harris Corporation bring together a broad base of experience in systems integration. Boeing brings to the table integration of complex systems and unique expertise in 6 degrees of freedom simulations. Harris complements our experience with its core expertise of large and complex deployable structures and mechanisms. So, you may be asking yourselves, why is the space station assembly relevant to the capture of an asteroid? As we celebrated the 50th anniversary of the space station on November 20th, just yesterday, we are reminded of the magnificent accomplishment. In order to assemble 43 flights incrementally, 35,000 pounds at a time, it required the amalgamation of several disciplines working together. Assembly mechanisms, targets, cameras, robotic arms, simulations, dynamic analyses, and the human element were brought together each flight for it to be completed successfully. So this assembly experience has allowed us to learn and work complex tasks in space, and particularly assembly tasks. It is with this background that we offer several concepts to meet the asteroid capture challenge. One of these possible concepts is shown here. Deployed from an asteroid retrieval vehicle platform, booms with multiple compliant arms are to snag the asteroid. At each joint, as you see in the graphic, there will be microsplines in this concept that will conform to the asteroid soil. And at first, self-capture itself to the asteroid with mechanisms deployed from the platform. After the arms, and after that, the arms and the ordnets that could be used can snag the asteroid. Then the platform will permanently be attached to the asteroid. The goal is to capture the asteroid and leave it fitted with a platform that would have, for example, as you see on the left-hand side, a grapple, a robotic grapple fixture attachment mechanism, or it could be fitted with a NASA docking system for future visits to redirect the asteroid or for human exploration missions. Boeing teamed with Harris primarily because of its expertise in large deployable structures. Seen in these photographs is the reflector that was fielded by Harris for the ACES commercial communications satellite that is currently in operations on orbit. The type of reflector that you see being deployed here is 12 meters in diameter in the final deployed configuration. Harris is also working in constructing a 22-meter diameter reflector of the same type. We know that several of the concepts studied for asteroid capture use large deployable structures. Both Boeing and Harris believe that these mature and proven technologies should be considered as candidate for asteroid capture concepts. So let's discuss for a minute the challenges, and there is quite a few. The asteroid capture mission has tasks that are challenging, but we believe that these can be solved by leveraging from space station experience and available technologies. The autonomous capture execution challenge can be met by designing integrated intelligent systems. Because of the uncertainty of the asteroid surface, shape, and soil composition, capture systems must be highly adaptable and be able to be reconfigured to conform to the surface. To select a suitable capture site, and for control reasons, the uncertainty in the knowledge of the center of gravity of the asteroid will require that we survey, characterize, and understand the composition of the asteroid before capture. Capture will also require the capability to decouple the loads, and I believe that's one of the items we were discussing a moment ago, imparted by the rotation of the asteroid during the initial attempt of capture and later during the D-spin. Hence, the center of gravity and other tensor data will need to be integrated into the control system and the simulations that will enable the capture. During the capture, there will be interaction between the capture and the spacecraft control systems. Due to this uncertainty as well, several simulations must be performed ahead of time, prior to capture, and real time during capture. Overall, we believe that we can meet all these challenges, and together working with NASA, it will allow to fulfill the asteroid capture mission.
Very good. Do we have any questions from the floor, Mr. Enriquez? Do we have any questions online today? No? Okay. Very good. Let's give our presenter a hand. So what we're going to do is have another slight pause because people are moving between the sessions, and I want to stick to the stated time. So our next presentation will be at 9:45, so you got another 5-minute pause break. Thank you, Mr.
Oh, thank you.
Okay, we're going to get started again in the Capture Systems session. If y'all can take your seats. Our next presentation will be from Harold Garish of Marshall Space Flight Center, and he'll be discussing momentum exchange tether to D-spin asteroid.
Hi, good morning. Like I said, my name is Harold Garish from Marshall. Co-author who helped with this quick look was Les Johnson, who at Marshall has had lots of years experience with tethers. I'm going to kind of go over the physics that we were looking at, what kind of size tethers, a possibility of capturing the asteroid, what the D-spin sequence would look like, a possible ground demo, to demonstrate the physics, and then kind of roughly the technology readiness level of some of the systems. Okay, so I haven't been fully involved with the asteroid retrieval mission. When we heard that this RFI was out, we just did a quick look to see, is there this possibility that could help take the spin out of the asteroid? We used 13-meter diameter, 1,000 metric tons, maximum 2 revolutions per minute, and just to see what kind of tether length and size of end mass is needed. Okay, and so the goal, we're going to de-spin the tumbling asteroid to a level that the asteroid redirect vehicle can handle. Now on this chart, or on this pitch, I kind of call that a mothership, but to take the load off of that vehicle, to dissipate that energy that's in the spin. And so basically what we're doing is releasing a small mass, deploying it from the surface of the asteroid, letting the spin rate go down, and then when it goes down to an acceptable level, then we can separate this system, and then the asteroid retrieval vehicle can take it from there. And so we're using angular momentum and changes in moment of inertia from doing this. Okay, this is showing what kind of length is needed in the tether. Each of these different curves is for a different end mass, and the goal of this plot was to see if we brought it all the way down to 0.2 degrees a second, and this is how the effects of the asteroid mass pull comes into play. But you can see it's less than like 4,500 kilometers for these assumptions. This chart over here shows how that rotation rate, if it starts off at 12 degrees a second, how that decreases as the length of the tether increases. And you can see that most of the rate goes down, like 1,500, 2,000 range, and then to fine tune it, if you want it to bring it down to like that 0.2 degrees a second is where you would have more length added. So there's flexibility in the length of the tether and the mass. I mean, the tether they both work together. If you have a smaller mass, you're going to need more length, and vice versa. But it also gives you, I think, variability on the range of asteroids that you could use this concept on. So a single concept could apply to a range of masses as well. Okay, and then this shows the tension. As the tether length increases, there is tension on the tether, but then it starts to go down because the rotation of the asteroid really starts to come into play. And I think like this number, like 700 newtons, is it's about 160 pounds roughly of load. And again, all these curves are for, each color curve is for a different end mass. Okay, now the capture concept, right now, how do you get the end mass on the asteroid to start off with? And so having a small separate craft that would take this kind of capture net to the asteroid, have inflatable support struts that that would guide the net around the asteroid, and then it would collapse around it, tighten the attachment of this mass to the asteroid. Okay, the sequence of how this would work is you have your mothership, with your small craft would separate off of that. We come out to the asteroid, deploy the capture net, have the capture net collapse around the asteroid, and then tighten up. And then the small spacecraft that got you, to the asteroid, or got the net to the asteroid, then becomes your end mass. And then you let that come off with a deployer, and then to slow the spin rate. And then when you get to acceptable low spin rate, then you can separate the tether and the small craft, and then the mothership can do the rest. But like I said, this is a quick look that we were doing. I haven't been involved with the asteroid redirect vehicle as to what operating boundaries it has, but I'm just pointing out this is just a general concept, and there's variability on how far down you can take that spin rate. Okay, ground demo. This is a flat floor. It's at Marshall. It's 44 by 86 feet, and they do a lot of two-dimension like docking maneuvers, or there was some work they had done with small spheres testing at tethers in the past too. So everything's kind of on an air cushion, and so you can simulate in 2D how docking or how maneuvers can take place. So this concept that I'm talking about here, we could do also on the flat floor. I mean, this is just an example of a large rig they have. I think it's over a ton. That's on air cushions that can spin around. You just barely touch it and it'll move. So it may be a way to also demonstrate the physics of deploying this in mass and showing how much it pulls off on that spin rate. My background, I've done a lot with solar thermal propulsion in the past, and so when we looked at how to deploy, inflatable struts, I was just showing some, experiences I had in the past. This picture right here is the LaGuardia flight experiment done in 1996, 14-meter diameter antenna. This was a Spartan vehicle that it was deployed off. The picture was taken from the, from the shuttle, and I think the length of these support struts were like 90 feet. And so when I first saw this years ago, I thought, well, boy, it didn't get tangled up. I mean, it deployed, without that. I mean, there's other difficulties that the antenna had, but just to replace the antenna with a net, and I'm saying about the general size of what we're talking about here seems to be, similar size that was used in the past. And then this shows, ground deployment tests that were done. This was another activity that FICOL SRS had done with support from the Air Force, looking at deployment of an inflatable antenna with support struts, torus, everything. They did it 4 times, and the variation was like a half an inch, based on 4 go-arounds. Okay, and then tethers. There's been numerous flight experiments, ground demos, with electrodynamic tethers, momentum exchange tethers. The lengths that were used in the past, this SEDS experiment had a 20-kilometer, length tether used. Some had a 4-kilometer. This TIPS experiment was in orbit for 10 years, for a survivability kind of test. So I just wanted to point out that tethers have had lots of work with deployment mechanisms, how to keep tension on. So that's why the rate that you release this en masse, you have control over. So that's another variable that you can work with. But I just wanted to point out, the last page and this page is that there's a lot, I think, similarity of TRLs with what what you're all trying to do. And I think that was it.
Any online? Okay. So anyone who'd like to raise a question from the floor, you can step up to the microphone. Do we have any questions? Yes, sir.
It looks like the point where you attach the tether relative to the spin axis would be crucial, and the further away from orthogonal to that, the less effect or potential detrimental effect you might have. Have you looked into that?
Right. You want to, I mean, for this to work at its best is that you would, the spin axis, from this picture would be coming out of the page. So you'd want to, attach, right on the, 90 degrees, to that, get the most out of it. We haven't, I mean, this is just a quick look at, just, a first look. We can look at, if it was at an angle, or if you didn't have just a planar spin, impacts of that. But we were just looking at, is this even doable? And it looks like it is. It looks like it's within the boundaries of what can be done. But how much of a savings is what has to be looked at? Did that answer your question? Okay.
Next question.
So the maximum length of this tether is not very long, right? This is tens of meters or?
No, the tether in kilometers, and so that's why it depends on how far you want to reduce that spin rate. What do you want to bring it down to? And it's also, if your end mass is larger, then you don't need as long a tether either. So that's why there's a playoff between the two.
So what length do you have to start worrying about arcing in deep space? That's a lot less than in low Earth orbit, right? Because you're a lot longer rather than in low Earth orbit, because the environment's more benign, but it's not totally benign.
Right. Well, it's the other thing. How long would it take to do this? And I don't think it's going to take but a few days, to do. But issues or situations with the inflatables or even the tether, the length of time that it's actually going to be exposed, right? You got other space environment effects, but I don't think where this is at, you're going to have the same ones like you do in Earth orbit, but still the time that you're actually using is not going to be, it's not like weeks or months kind of thing. And like the inflatable is just going to be inflated enough to get the net around it, and then you're done with that.
Thank you.
Okay, one online question.
And it's basically, what would happen to the asteroid capture spacecraft after it separates from the asteroid?
It would just go wherever. And see, that's where the mothership can be 90 degrees off. So, I mean, it would be right there in close proximity, to the asteroid, but it would just be, not on the 90 degrees to the plane of that spin. But otherwise, when it's cut, it's gonna be off on its own.
Okay, thank you. Any other questions from the floor? Anyone else? Yes, sir.
Did you compare the extra weight of the tether and the additional spacecraft to what it would be replacing in terms of the propellant used for the other methods of D-spin?
We didn't look at other methods, but, roughly I think it was like 150, 250 kilograms. I mean, there's some variability, there on that mass. I mean, like I said, this was a quick look. We didn't get into the, real detailed design of what this little spacecraft would be like. But the mass of the tether, I don't think is going to be that, that much. Okay.
Okay. Thank you very much. So we're going to take another 2-minute pause, but we'll let our presenter get in position. So another 2-minute pause to stay on the schedule. Okay, we're going to pick back up here. Our next presentation will be from Jeff Slostad of Tethers Unlimited, and he'll be discussing NanoSat Deploy Net for Capture Asteroid and tethers.
All right, sorry, those of you that were hoping to see Dr. Hoyt, he could not make it, but I was here for most of this work. It started about 13 years ago. Actually, it started about a week before I got here, so I missed one cool thing, but we got it all covered here, I think. We'll see. This is very similar to the previous presentation you saw, so I'm not going to spend a lot of time talking about the math and such, but I think, as has been mentioned many times, we were looking at the issue that a lot of the interesting asteroids were what some people are calling fast rotators, which really is just rotating. It's a problem. It's a serious issue. You have to de-spin somehow if you're going to keep your system working properly. We looked at kind of what are those challenges, what are the risks, and how could we mitigate those, and we realized that some of the work that we'd done previously with trying to bring back non-cooperative spacecraft to deorbit them, we could apply that technology to this problem and kind of get a real simple high TRL solution. And it's essentially, like you just saw, a daughter ship that grabs on, that performs the capture and the de-spin, and then releases itself. Real straightforward. It could be used as a tow rope. We don't think that's really the right approach, but you don't have to let it go. But anyway, you'll see that the simple approach is you launch the small spacecraft. After the small spacecraft has been deployed, bring out so you're aligned with the spin axis so you can see everything, and if you're remotely controlling the small spacecraft, you can do that, or you can just see what's going on, or more importantly, get out of the way, because a long tether is going to start swinging around pretty quick. The system, which again, you've seen graphics that look like this all day. This is actually a picture of hardware, though it looks like a graphic, but that is hardware that we've tested. That deploys out using inflatable booms, deploys a net out. We chose a net because, well, it's just easier to see what's going on, and for the initial applications where we were just trying to grab onto spacecraft, it worked fine. The main reasons for going that route for us were a net compacts much smaller, and we were looking at using very, very small, like CubeSat scale spacecraft to grab onto very large spacecraft. So though we looked at using a bag or something of that nature to capture debris, it just doesn't pack as well as a net, which can have a very sparse, low density construction. I also worked on a fishing boat, and this was my comfort zone. This is kind of where this whole concept came to us 13 years ago, is I was like, oh, I know how to grab onto something. I put a net around it, and then I cinch the end. That's real easy. So that's kind of where we came up with this approach many years ago. You can see it just grabs on, the net cinches up, and now it starts rotating. And at this point, we really don't care if it's banging up the spacecraft a little bit, whatever. There are some elements in the way that the booms terminate that will give some stability, but rather quickly we're going to start deploying the tether. Now I say quickly, we're going to start deploying the tether soon, but the deployment itself is probably going to take on the order of days. It's going to be done real slow, real gentle, and it's essentially a yo-yo de-spin device. There's no fancy math here or anything. I mean, there is. I think there it is right there. It's not that exciting, and I think there is a typo here. I think that relationship gets it down to 0.1 degree per second. The system, again, previous presentation covered all this, so I really won't get into it too much. See, it's pretty straightforward stuff. At the end, we say just let it go. You can imagine, again, for graphical reasons, we used a net in this picture, but if this was a membrane instead of a net, you basically have now grabbed onto the thing, you've bagged it, you just come up and dock with that. There's nothing else to do. There's not a need for another enrobing process. We've already bagged it up and sealed it up. So the end body, the anchor element, or where we released it, is where you would grab onto it with the mothership. And there you can see it docks to the end of that net. And again, this is the artist's conception. This is a picture of real hardware that we built. This is, if you're familiar with it, this is sized to be a 3U CubeSat. You can see it's a paintball air tank sticking out the end because it was just some prototype hardware that we built. Developed a long time ago. And it, again, used inflatable booms because that seemed to be the simplest way to make something that packages very small. I think there've been a lot of interesting approaches that have been described here. I don't think it has to be an inflatable boom, but this, for us, for making a very small, compact system, this worked very well. And by properly making the boom, we actually get this natural arcing shape. It worked out really well. So again, because of my background, I just said, well, we'll just cinch it around the end. But the cinch lines, which come from the winch in here, go up here and then connect between the three arms. When it gets done cinching around the end, then you release the gas from the tubes, and then it collapses and just grabs on and holds very tightly and makes a very strong capture. And here is some testing, and I hope the video's not playing because it's just terrible. We'll see. Okay, I'll go hands off. So here's an early test, and this was kind of an early flight on a Zero G Corporation flight. It was it was actually their very first tourist flight. I think their second day of operation. And you can see it was pretty straightforward. We were limited on how big we could build the thing because of the size of the aircraft. And then on the other picture there, you can kind of see in the lower right, you can see the picture from inside the capture thing, picture-in-picture thing, and you can see how it grabs on. And once it grabs on, it's okay that the thing bounces around in there for this application. You might want to do a little bit quicker winching if you've got a big rock in there, or particularly if it's a loose pile. Like I say, we did test this in Zero G. We thought the next step after this would be to launch something, so we were ready to go at that point. And I guess the debris remediation threat went away. Not really. We've been ready to fly this mission for quite a few years, and I think maybe the current interest in this other application might be a good way to do that. But I'll get to that in just a second. I forgot I had this slide in here. This is another video, if you can click that one. This is for despinning a large inflatable habitat with a 1 kilometer tether, or 1 kilogram tether module that was essentially, well, for branding purposes, it was designed to fit in about a 1U CubeSat form factor, but it was really a 7-Up can. And so it was a very small system, and this is obviously a sped-up simulation. At Tethers Unlimited, we have quite a bit of tether simulation experience as well as a lot of hardware experience, so we kind of mix both, and we work with the guys at Marshall quite a bit. Yeah, I think one of my pictures was in the presentation we just saw of the Zero G test. That was my hardware being tested by one of my engineers. Anyway, that's kind of getting boring. The point here, though, is that a real small, simple tether system can despin a very large object. You see this with yo-yo despin devices all the time. It's really not a huge problem. I do agree that there is extra challenge when you say, all right, now I'm going to have 2 spacecraft, but in reality, if we're going to go out and exploit asteroids and interact with the solar system, we've got to be willing to step up to having a small spacecraft that's part of our system. I just don't see that as a valid concern that, oh geez, more complexity. This is this is NASA, right? Let's do the hard things. Here's a little bit more on some tether stuff. Here's about what we're looking at for a tether spool. Oh yeah, okay, same picture as you saw previously. This is a tether deployer that we did that was it was a braked tether. we'd launch out an end body, and then there was a kind of a pinch roller tortuous path mechanism that deployed out the tether in a controlled way. Here's our tether deployer off of a 3U CubeSat experiment we did a few years ago, quite a few years ago, 10. Here's a kind of interesting experiment working on right now, and all of you that are at JPL that want to help support this stuff. This is a phase 1 SBIR that we're turning in the phase 1 final report and phase 2 proposal tomorrow, and it's for an asteroid sampling mission, but a lot of the same technologies. We launch out a tether and then we reel it back in with the sample. Kind of fun stuff we're doing again with JPL. And again, I'm just going to point out the high TRL of this. It was mentioned earlier that we need to look for some early experiments that we can kind of get the momentum going and make things happen. We really believe that we've got something there. This is what we consider our plan, our validation approach that we could put together fairly quickly, and this is kind of where we were evolving back in the day, is that we would test it on an upper stage. We would essentially have an upper stage, end of mission, we would launch off of that upper stage. It would use the remaining fuel, the residual propellant, to spin the thing up, and then we would come back and just grab it. Real simple, real straightforward, and then let the thing out. And we could do all of this in a 3U CubeSat. Be a little roomier if we did it with a 6U CubeSat. And realistically, we could do this within 18 months, 2 years. This really isn't a huge stretch for us because it's relying on a lot of technologies that we already have developed. It wouldn't require any special launch systems. Again, if we used a CubeSat form factor, we could, basically just use what's already there for launching spacecraft. And this is kind of a notional concept that uses a bunch of equipment that we already have. We've got a electrolysis-based thruster that is finishing up within the next couple months. It's being flight qualified, uses water and electrolysis to make things. We've got a deployable array that we built for the Army. It's 85 watts. Folds up again for a CubeSat. We've got a gimbal that was made for the deployable array, but also can be used for the thrusting. To do that move where you've let go of the small spacecraft, but now it's actually got to get over and grab onto the large spacecraft. Now, initially we looked at having the host spacecraft come up and put the net and then back away real quick. That would be a simpler approach, but now you have to build the large spacecraft. And we believe this would be a near-term validation approach that would be pretty straightforward and pretty easy to do. And I think that's it. Any questions?
Okay, we're ready for a question from the floor, if anyone has a question.
So have you given any thought to how well this tether system is going to work for a tumbling asteroid, one that's rotating on more than one axis?
Haven't thought a lot about it in our modeling. We went pretty straightforward with that, but I really don't see that as much of an issue. It's really just a moment arm thing. It's still going to spin, and as long as if we're coming off the side and there's no moment arm because we're just wrapping around this way, that would be really improbable that you would see that condition purely. If it was pure spin, we'd put ourselves properly. If it was a combined thing, we'd take out most of it in one, and then there'd be a little bit of a moment arm issue in the other axes, but I think it would despin. But I think that would be a great simulation effort to look into fairly soon.
So you think most of the rotation would be in a primary axis?
I think you could find a good capture point that allows you to deal with the majority of the energy. Brian's simulation showed some pretty cool stuff. I was showing how the different axes line up. I believe you could do that. It's not my strong point though, and I would definitely defer to people that could perform the modeling and give some better feedback. Brian, maybe you? Thanks.
Yeah, I think that you're right. There certainly exists a point somewhere on the surface, in fact, a whole annulus of points that where you could basically despin, and detumble from a mass, a yo-yo, basically at that point.
Yeah. Cool. Thanks.
One more question.
So, just one. Right, so you're going to be doing this a few light minutes from the Earth at least, and you have these two spacecraft. Have you tested doing this autonomously? Does this require like close communication with the Earth, or can this all be done up there by itself?
One of the reasons that we chose this approach was because we wanted to be able to do it autonomously, and to me that means something that's very forgiving. You need an opening that's large, you need something that's smooth and capable of just kind of being very forgiving. And I believe that you could do that pretty straightforward. And where you saw the picture-in-picture video, that was basically trying to assess how well we could target something just using a bore-sighted camera right in the middle of the arms. And it looked real easy. At the time we were working with SAIC, and they pretty much said, yeah, don't worry about that part. If you can see it, you can see. I wish we had another video. I think I might have it on my laptop that shows a simulation of a targeting thing. It looks very, very, I don't know, Terminator-esque, in that here's some crosshairs following it around, but it should be pretty straightforward to capture this large object. It's the only object in the field of view. As long as your arms and your opening on your net are large enough to accommodate your lack of ability to target.
All right, well, thank you.
Yep.
Thank you very much. So our next speaker is Alan Lowry from Airborne Systems, and he'll be discussing air-beam inflatable tubes for deployment of capture bag.
So I am the inflatables guy you were worried about offending. I'm not offended, and I think when you see our presentation, you'll see the kind of inflatables that we're talking about are really non-traditional and very well suited to this application. When we looked at the requirements, we did an assessment, and these are some of the top-level requirements, and we thought that this lended itself very well to a technology that we have called AirBeam, and I'll describe that a little bit later. But large deployed size, and our concept looks similar to some of the other ones we've seen. It's approximately 17 meters in diameter, the mouth of the opening. But yet it has to be packed into a very small volume, densely packed to a size that fits within the payload fairing of the rocket. Has to have very high strength and high stiffness. When it's deployed, it has to be a very predictable geometry. It has to have sufficient stiffness, and it has to absorb the transfer momentum from the asteroid to the spacecraft. In other words, it has to be very strong to deal with that, the loads and momentum that be transferred through this structure. It has to be durable, and this bag is going to be in friction with this asteroid. There's going to be relative motion there, so it needs to be able to handle that abrasion that will take place in that friction. Also, a very important attribute of this is it needs to be testable in 1G. It needs to be a very reliable system. There's going to be a lot of money at stake here, and this thing has to work. And so it needs to be able to be tested on the ground, 1G, and maybe be deployed multiple times to prove that it works as expected. Also, has been mentioned many times, has to be a high maturity, high technical maturity, and something that can be developed and demonstrated within a period of 24 to 30 months or so. And so I'm going to talk a little bit about what is an AirBeam. So one thing I learned in kindergarten is to bring show and tell. So this is an AirBeam. This is a braided structure. The fibers could be Kevlar, Vectran, Technora, Xylon, the Aramid type fibers. And it has a gas barrier inside of it. And the unique feature is it has axial members, axial cords, axial straps. And that's what gives it the bending stiffness. This is probably inflated to 5 or 6 psi, and it's a very stiff structure. And I can buckle it, and it returns to its original position without any damage. And so as we talk about this application, a lot of load would go into this structure, and it would have to deal with a lot of, it not only does it have to be stiff, but it has to be compliant as well, and not result in severe damage or, ruin of the structure. This technology is very dimensionally stable and accurate. We can predict very closely what the deployed shape is going to be. It also can be designed to change its shape in relation to the inflation pressure. Also, as you can imagine, with these axial cords, if I shorten the cords or straps on one side, lengthen them on the other, I can create a curved surface. Or I can create ultimately a torus with this technology as well. And you can see the various applications that we've used in the past at Airborne Systems. We've built over 10,000 of these air beams. Some of them, upper left-hand corner, that's for a terrestrial shelter that has inflatable air beam structure. Those are approximately 80 feet in width for that structure, about 40 feet high. The one picture there shows the air beam supporting a Jeep, hanging a Jeep from it. We've made tori. We're currently under contract with NASA Langley to build inflatable aerodynamic decelerators. And the picture at the bottom is the Irby 3, which is a 3-meter diameter aeroshell that was launched last summer. And it was inflated in space, deployed and performed very well. It achieved Mach 10 and demonstrated that it met all the objectives. Okay, our design again looks very similar to some of the other ones. In looking at the potential geometry of the asteroid, we created a funnel type structure that could accommodate a wide range of shapes of asteroids. Although we looked at several different concepts, some using inflatable tori and so on, we thought this was the most promising concept. It consists of 6 inflatable air beams that have joints or knuckles, if you will. They're about 18 inches in diameter, about 19 meters long. The asteroid containment bag, again, is a Vectran material, very resistant to abrasion. And so as the air beams deploy, they put that bag in tension and hold the bag open to its required geometry. We've included an impact attenuation device at the lower end that once you contain the asteroid and pull it into the spacecraft, that would mitigate any kind of impact loads to the spacecraft. And then in the base of this would be housed cinching motors, possibly 3 of those, and the inflation system, which would consist of nitrogen gas. Our estimate is about 400 kilograms. This is a very rough estimate, not really understanding fully what all the loading might be. We think it's conservative. In the right-hand corner, you can see the structure in the cinched configuration. And so with these winches, we have circumferential winches, not winches, but cinches. And so we would have one at the mouth and possibly one part way down the structure. And once the asteroid is enveloped, those cinches would be pulled tight. We would envelop, and in that process, these beams probably would buckle. And that's why I kind of pointed that out, that in the right-hand corner picture there in the cinch configuration, you would have some buckling and compliance of the structure, but it would be able to tailor itself to fit the asteroid and be able to take the load that would be imparted in it. It could be torsional or lateral loads, and once that momentum is transferred to the spacecraft, the system would sort of realign itself and center the asteroid to the spacecraft. A couple of key features here I just want to point out that this technology is very scalable. So, we can build a small beam like this. We can build beams that are 36, 40 inches in diameter, many meters long. And so we could very easily design and fabricate a scale version of this for early testing. And in our development plan, we proposed a quarter scale, could be a 1/5 scale to match up with the JPL system. But that could be fabricated very early in the development process and advise the critical design review, really substantially reducing the risk. So that could be used for packing, deployment test, actual asteroid, simulated asteroid capture maneuvers and those kind of things very early. The second thing is that since this is a very stiff structure, it can can be used very easily in 1G environment. And we're proposing a proto-flight system. In other words, the qualification unit is also the flight unit. And so this unit could be packed, deployed multiple cycles, and go through all the typical testing you would want to have it go through to prove out the reliability of the system. So with that, I'll just open it up to questions.
Hey, do we have a question from the floor? If you do, please go up to the microphone. Yes, sir.
Several people have discussed the scalability of these various concepts, and you also, and when I look at the mission as defined by NASA, and we're talking about this relatively large object that we're all struggling to figure out how we're going to de-spin it, is there really that much value in grabbing one large object? And, I mean, what's the distinction between the interior of that large object, which really doesn't provide you much value? Would it maybe be more valuable to go out and collect a whole garden of variety of smaller asteroids and deal with asteroid capture at a much more manageable scale?
Yeah, that's probably not a question for me.
Well, this is a workshop, so
yeah, it's a workshop, so I'll leave that open to maybe Brian or somebody else to answer.
What I'd like to do is pick that up again in the group discussion at the conclusion of the presentations. Super. Okay, do we have any online questions? Okay. Any more questions from the floor? Yes, sir. One question.
So I thought that was very cool, but I was a little surprised at the end, your recommendation for doing this as a proto-flight. What was driving you to that recommendation?
Well, it's certainly reduced cost and schedule, and so that was probably the primary reason we put that in there. It's certainly not necessary. If there's sufficient time and money in the program, we could build a dedicated flight unit. If that's what the program wanted to do.
Okay, so it sounds like, is this a very expensive proposition to make a crawl unit, another one, or it sounds like it's you're trying to
I would say
money.
not. I mean, I don't know for a fact what the expenses of some of the other concepts were, but this is very I would say less complex than many of the other concepts, and so I would think it would tend to be less expensive. That's just a thought process we had there, that you could do that with this if you chose to.
Okay.
Sure.
All right, any other questions from the floor? Okay, thank you very much.
Thank you.
So we're going to move on to our final presentation. Howard Eller from Northrop Grumman will be talking about asteroid redirection vehicle with SEP and Astromesh-based capture mechanism.
Sounds great. Thank you for the invitation. It's good to be here. Good to see everybody. I appreciate my position at the end, having been able to integrate some of the other presentations. And I think this is an integrated presentation. If you're not familiar with Northrop Grumman, we're a small aerospace company. We've done work for NASA. We're the JWST contractor. We did the Chandra and GRO. Great observatories, Aqua Aura, the LEM, the TDRS first generation, and the LCROSS. We also owned the Astro Aerospace deployable developer, and they have a very close relationship with JPL, and that is a very important tie for us. When we started looking at this low risk, and the launch date drove us to interpret low risk as being existing. So our intent here was to stitch as many existing pieces together as we could to get a system that would address the requirements. Another requirement that wasn't stated that we imposed on ourselves was we wanted to do minimal damage to the asteroid, if you will. So we wanted something that would not resurface it, that would preserve it in its basic intent and condition. And so I think what Brian presented about the dynamics is exactly the track that we were following here. So what we understood is that we have to address any kind of condition when we get there. Whatever it is, we got to deal with it. And so our system had to have a very wide bandwidth. And so if we sum it all up, what we basically came to is we wanted a system that would have both the features of a bag, if you will, and a deployable structure. And so we have proposed here a hybrid, and that hybrid is based on our Astromesh concept. We also wanted to keep the system as low weight as possible, and so when we looked at what it would take to launch it, we were wanting to be in the Atlas category. So others have covered this, and there was a session on it at the first day of the workshop. But there's a whole range of sensors that come into play, and you're acquiring knowledge as you're adjusting your orbit, and you're coming along the V-bar, if you will, co-orbiting with it, wanting to understand its makeup and composition further out, and then model the dynamics so that you know the rotation, and you can do like Brian showed, pick the point at the time that you touch it so that you are on the rotation axis and you minimize the tumble rates. And so as you come closer, you're increasing your modeling until you understand very closely what the structure looks like, and you pick a point, the point, based on probably dominantly the rotation rates of where you want to contact it. And so the system that we came up with uses an existing spacecraft. It is a Heritage bus. It has 1,000 kilograms of bipropellant. It has the capability for 6-DOF, pretty high agility. It's really, really beefy, so it can handle that initial jolt. It has 4 CMGs that can be used or not that are massive, so it can maintain lock on that point and then use its 6-DOF system to spatially stay over that for a period of time so that the capture mechanisms that we're proposing can fully enclose and grab it. And that doesn't take that much propellant. The piece that we're having to add, and that's the 4 tanks on the bottom, is the 12,000 kilograms of xenon. And so we have that as a module. And the way that we're proposing it here, that unit could then be used by any other spacecraft manufacturer. Could be inserted below their spacecraft. And so there's a big impact to industry that's transferable across the whole industrial base. So the basic system looks like this. We take the Astromesh reflector, and we're using it in 2 ways. One, the Astromesh is really unique in that it's a 3-dimensional structure. So when it's assembled, you can pick it up, rotate it, you can kick it. It's not fragile at all. It has very high frequency and high strength. So we're using it here as 2 25-kilowatt wings where we suspend the solar array material in the middle, and then we're also using it to create these 2 half capture mechanisms. So the surface there acts as the bag. So that's part of the hybrid. The other part is that you can close this very quickly. In fact, if you want to abort, you can move it away. What we don't want is as we approach the asteroid, which is all done autonomously, it contacts the edge and then it starts rotating and you get something tied up in itself. So that's what we're trying to avoid. So we want to be able to close quickly. We want to be able to rehearse that and gain knowledge. You're going to see a sequence in the next chart where we do an Apollo 8-like maneuver to show that, yes, we can maintain lock. We do an Apollo 10 where we touch it, and then after we've done it, then we actually grab it. And that's one way to do it. And so what happens is there's a conical structure that contacts it. That conical structure can be moved. It's also instrumented. It can be used to take samples. and it positions the asteroid where we want it in the astrocapture devices. The device closes and locks, and then cinching cables snug it tight. You turn off the ACS system and let whatever happen. Once you verify it from the ground, you activate it again, and for a very small fraction of your propellant load, you can completely despin the system. So this is sort of our, here you can see the rotation, primary rotation rate, the precession and the nutation of that, and so you want to come in along that axis, and just like Brian said, you want to time it and make sure you understand the dynamics and recognize that those dynamics are going to change based on your influence. If you touch it, even your gravitational presence will have some impact on it. So you want to make sure that you understand what that rotation rate is, and then you can do your timing. So we have our 3 autonomous captures where we increase our confidence level, and then we come in and actually do the contact and turn the ACS off, like I said. Eventually, we then do the EP transfer. So I think the theme that we want to transmit here is that it's heritage-based. The Astromesh has flown 8 times, 100% success rate. It's currently flying on a SMAP, or getting ready to launch for a SMAP mission, and that is a dynamic system. It's rotating at very high RPMs. And not only that, it has to maintain a precision surface. So you don't have any of that precision element here. And so you match the rotation so that it becomes a much smaller problem. You're just grabbing it now because your spacecraft is rotating with the primary rotation rate, and then you're slewing during just that period that you're grabbing it. And then you can eventually then you bag it. And so now you don't send debris and you know what the condition is. So you only capture it after the asteroid is in place. It's where you want, and you have a abort capability if the system so chooses. So that's our input to the workshop, and are there any questions?
Do we have any online questions? Okay, we're open for questions from the floor. If anyone has a question, just step up to the mic.
John.
Go ahead, sir. To the mic.
So how quickly do you close this clamshell around the asteroid?
Less than a minute.
So, because it seems like you have to go up and you're bumping it with this conical shaped thing.
Yep.
But then you still take a minute or so to close around it. How does?
Well, we were actually envisioning seconds. So it's a very fast closure with the dampened final capture and latch. Wow. Okay. And then the main amount of time is then tightening your cinching cables. So our thesis here is it's a hybrid of both approaches. It's doing everything that Brian showed, and it's doing the mechanisms that MDA showed, but it's integrating them into a single system, so you get both of those benefits.
Do we have any other questions from the floor? All right, thank you very much.
Thank you.
So we're, again, running ahead of schedule, which is always nice. I wanted to bring up Brian Muirhead, who's been leading the JPL team in the overall redirect vehicle development, and he had a few charts he wanted to share with the group. After he finishes his talk, then we'll have an open discussion here for the remainder of the session.
Thanks, Andre. Appreciate the opportunity here. A little preface here. I'm going to talk about something that is associated with an alternate concept, and this is something that NASA has asked us to work on with the Langley team, as a team I should say. It was set up at Langley to look at what we call an alternate approach. Most of what you guys have been looking at have been associated with what we call the reference mission, which is, as Brian described, the concept of trying to capture a relatively large asteroid, a 10-meter class, 100-ton or 1,000-ton class object. But Dan and his team have been looking at an alternative approach, which is the idea of picking up a relatively smaller asteroid off a large asteroid, something that might be a few meters in size, a few tens of tons, and bringing that back. So that's a very different concept but it's also, based on what we've seen here today, I think there's a lot of ideas that you guys have thought about and proposed would be very applicable to that sort of pick up a rock sort of concept. So I wanted to share with you a very quick cartoon of a pick up a rock concept associated with using inflatables. And this really derives from some of our early work in inflatable concepts, and it applies very nicely to the idea of picking up a rock. So if we go to the next chart, the big issue here, the reason we kind of developed this idea was the concern that if you're trying to pick up a rock, the rock on the surface of an asteroid may or may not have integrity. It may or may not be strong. And we assumed, as we did in the original concept of the reference mission, that the asteroid itself is a rubble pile, and basically what Dan Shears talked about. So if you're dealing with a rubble pile, that's where you end up with a bag. And so now the boulder on the surface of a small or large asteroid, 100-meter class or larger, may or may not, in my view, be a cohesive body. If it is, then the manipulators and whatnot work really well. If it's not, then you're going to probably need something more like a bag. And those are things that we're going to have to study and continue to talk about with the experts. But what I wanted to just illustrate here was an approach that you could use to deal with a non-cohesive body, basically a small dirt clod, for example, in a couple meter class. So here you see basically the ARM spacecraft, but with a pair of smaller, relatively small inflatable capture systems with the objective of trying to grab a 2-meter object sitting on the surface of a large rotating asteroid. So this is a state that you might imagine the system in prior to the initiation of the actual proximity operations and capture process. So we go to the next chart, I guess maybe I can do that. So you would fly to a state where you're basically stood off at a certain distance. The sensors we're talking about using here, this basically the same sensors we would propose using on the reference mission. Cameras, but primarily closing the loop around a 3D LiDAR. So at that point, you basically have established the spacecraft attitude. You know what the target is. You've done whatever evaluation of the target beforehand and say, this is the one we're going to go after. Next chart. So at this point, this is where the inflatable begins. You basically inflate a stack of inflatable elements, and they could be, linear columns, things like, the airborne stuff that Alan talked about, or other inflatable designs. But basically, you end up with a 2-meter, or basically a 3-meter diameter capture volume with a bag that is stood off from the spacecraft by, say, a meter, with a more or less flexible, depending on how flexible you want that inflatable stack column to be. And you're looking down the center line through, with your sensors at the target as you approach. Obviously, this is a precision landing problem with reasonable precision, not really great precision. Closing the loop again around the LiDAR, you approach, and during this entire phase, this is all autonomous at this point. And this is what we would call a critical event. So at any phase, any point during this operation, the spacecraft has to be able to make itself safe. And it can't do it in the classic way where we just say we have a reset on the computer, we've got to go into a safe mode. You actually need to be able to back out of this condition at any time. You need to be able to return to a safe state, which adds to the complexity of the system design. Next chart, please. So you fly down to the surface, you basically have aligned yourself with the surface to some angle, and you're holding yourself down in place. At this point, next chart. So here you basically just close the mouth of the inflatable system. We've seen a lot of concepts that basically do something like that. Another assumption we've made here is that the rock is not really fully on the surface. It's partially embedded. So we've assumed we only grab part of the rock, maybe most of it, but the assumption is that we cinch around it, we grab it, and we hold onto the rock with the force that we're able to with the cinch system. Now if the asteroid or if that rock breaks apart at that point, that's okay. but if it doesn't, if we have to pull it off, we move on to the next step. We're held down with thrusters, and we maintain our attitude inertially with our reaction wheels. Next chart. Now this is really the interesting part, and again, where the inflatable really provides you some real special value here. We basically imagine a torus or individual spherical balloon-type features that basically inflate and push against the surface and push the rock off. So as you inflate in a controlled way, you're basically using like a pneumatic jack to basically pull the body off the surface. So next chart. At that point, you're free to fly away, and that's what you do. You fly away. Next chart. And you complete the cinching process. You cinch the bag around the rock material, and then you complete the cinching process with the final, next chart, last chart, pulling this thing all up to the spacecraft. So again, this was a different type of mission than the reference mission, and Dan and his team have been doing a lot of creative work in developing a variety of ideas, and I just wanted to get this idea out as a possibility, and something I think that Andre and Jason, as we look at the output of this session, can bring ideas that can apply not only to the reference mission but also to the Pick Up a Rock mission. Thank you. Appreciate the time.
Very good. Thank you, Brian. All right, we're at the open discussion session to kind of provide a seat input there. If I could bring my presentation back up, please. So tomorrow between 10 and 12, each of the sessions are going to do a report out on the discussions, and we have only a limited amount of time, so again, we'll be probably trying to focus on the highlights, but we were asked to explore a couple of questions and try to synthesize and come up with what we thought were the best nuggets that we can bring forward. So if I've got kind of a starter list here. I want to advance the charts, a couple of charts. One more. Okay, here we go. All right, so the first chart we're going to have is a summary of the most promising ideas, including their innovativeness and potential for improving the mission and system performance. And so from my review of the presentations, what I wanted to focus on were which concepts achieved the reduction of the spinning or nutation of the asteroid with the minimal mass and structure. So we've explored a couple of concepts here. So it looked like, from my quick read, that the tether concepts were probably the most innovative approach to doing that. It's somewhat different from some of the other ideas that are leveraging off of concepts that are in use today, as Howard mentioned from Northrop Grumman and some of the other industry participants. Inflatable concepts have more mature ground systems performance, and at the time when I wrote this, I said less maturity for in space. I had not looked at the Marshall pitch that closely, so I didn't realize we had done at least some DTOs back during the shuttle program. But we're certainly have a lot of test experience on the ground that our friend from Airborne mentioned. The deployable structures and robotics concepts, I think, could provide potentially greater control authority. I think certainly if we're dealing with a monolithic asteroid, that's definitely an advantage. But I noticed their mass numbers in some of the presentations tended to be a little higher, and I think Scott Bellman had brought that out as well. So it's just a trade, I think, at that point. So this was kind of my quick look at all of the different systems, and these would be some themes I want to try and bring. Let me click through these last two charts, and then we'll come back and open it up to the group for discussion. So if I go to the next chart. Okay, and so the next one was relationships or linkages between the ideas that could help with concept integration. You might look at combining some of the elements like the tethered base free flyer with an inflatable system, and in fact that very idea was brought forward, I think, by a couple of the presenters today, to use the tether to reduce your spin rate, and then the securing with the inflatables, and some of the anchoring system concepts that the Honeybee folks talked about could also be combined with the tether systems. Next chart. And then the last question was, what steps were we looking at? And right now, the agency isn't planning to do any detailed studies with capture systems. Brian mentioned the alternate mission concept, but I don't know if we're going to dig into the details that we looked at in today's session. We just don't have anything on the books right now. Okay, so let me go back to the top level slide. One more. There we go. Okay, so what I'd like to do is kind of this was a seed input, and what I'm interested in is hearing from the audience. And we had one gentleman who raised another question earlier. If you could come back to the mic and just bring your question back up, I'd appreciate if you could start our discussion.
Yeah, thank you. My question essentially had to do with the scale of the object that we're going to get, and the scalability of the technologies that are used to go and capture that thing, and the relative value of collecting one large object and exploring the surface of it versus collecting many smaller objects and essentially having more of a cross-section of different types of asteroids that might be both easier to capture as well as offer more science value.
So Brian Wilcox, could you give us a little perspective on that? And then maybe Brian Muirhead as well from the alternate.
Yeah, certainly getting a variety of objects would be great. The problem is that space is a big place, and they're not generally in the same orbit. And so when you find an object, in an orbit that is suitable for this mission, which, let me just remind the audience that, we need a V infinity with respect to the Earth of a few kilometers a second or less. And that's only a small fraction of the total objects, well under 10% of all the asteroids, near Earth asteroids are in that category. When you find one, the chances of finding a number of them in kind of the same orbit would be very unusual. And so you're kind of stuck with, picking individuals in the sky and saying, okay, we're going to go after that one, because the delta V to go to many in sequence would be very large. So typically the outbound delta V is 3 or 4 kilometers a second, but the return delta V is only 150 meters a second. That is, you only change the velocity of the 1,000-ton rock by 150 meters per second to get it to do the lunar gravity assist that captures it into the Earth-Moon system. And so if you had to pick up a rock and then do another several kilometers a second to another rock, that would be just prohibitive.
And Mr. Muirhead, if you could give us a thought.
I'll give you the non-technical answer. That's a very different type of mission. You can imagine that at some point NASA would say we would like to do a multi-target science mission in which we use solar electric propulsion and fly to as many targets as we can, and maybe we could do several, but you're not talking about bringing back a lot of mass. So you'd be bringing back relatively small objects and picking them up, and maybe it would be a relatively long mission. But you take something like OSIRIS-REx, which is to a single target, you could imagine going to multiple targets. And so that is, again, a very different mission than what we've been asked to do with this mission, which is to bring back, a significant piece of an asteroid or a full asteroid to cislunar space for human exploration.
Thank you, Brian. Okay, so now it's going to be pretty free-form. What I'd like to spend at least the next 10 or 12 minutes doing is just asking for anyone who wants to share their thoughts, your own integration, so to speak, of what we've listened to this morning, and just share your thoughts about where you think, in terms of technology development, or what we might want to consider for this. So please go ahead.
Marshall Eubanks here. So I had a couple of thoughts, literally. Things I didn't see people mention. We know that about 4% of the NEOs 4% of the NEOs are known binaries. So the actual number of binaries is higher. I would say probably 10 to 20% is a reasonable number. And unless you do good radar in advance, it's unclear whether you'll be able to detect that before you actually send a spacecraft there. So I think people need to think a little bit about the implications of going to a 100-ton rock and having a 5-ton rock orbiting around it at maybe, a meter a second or something like that. Fairly slow velocity, but certainly not anything you'd want to hit your spacecraft with. So that's one thing. Oh, and you might, and I think personally, just to say, well, we're going to go all that way, and then, oh, it's a binary, so we can't do anything, is not really the acceptable answer there. The acceptable answer might be, we got to know before we go, but to just say, well, we'll can the mission, I think is just not that politically acceptable. And the other thing is, the typical rotational velocity of the equatorial matter on these bodies is about 10 centimeters per second. They tend to be fast rotators. Now, of course, you could systematically go to a slow rotator, but if you just pick one at random, like, for example, ones that have low delta V relative to the Earth, you're likely to get something about 10 centimeters a second, and that's a reasonable number either for the tiny guys, the 1 or 2 meter guys or 5 meter guys that spin more rapidly, or the 100, 150 meter guys where you're going to pick a rock off because they tend to spin a little slower. Okay, so you need to think a little bit about debris flying off at 10 meters a second, and might that hit your spacecraft? You know, how do you want to avoid that with your other? If you're going to have 2 spacecraft, how far away you need to put it? You know, does it need to have active avoidance? I mean, I think in principle you might be able to predict, but you're talking about things that are oddly shaped, that have odd, potentially odd internal stress abilities. There may be rubble piles with van der Waals forces that stick here but not there, all that kind of stuff. So you don't really know where debris might go. And it seems to me, most people wouldn't want to have 10 pebbles thrown at their spacecraft at 10 centimeters a second. It's fairly slow, but it's not that slow. And
okay.
So those are just 2 things I didn't hear anybody mention, and I think people need to keep them in mind. So even if in other words, just even if you're grasping around a small body, you may not grasp that cleanly. A little bit may get away, and so you still may have debris flying around at those kind of velocities.
Okay, thanks, Marshall. Appreciate it. Howard?
Just a couple of points. One would be a theme that if it isn't a rubble pile, the capture mechanism or approach shouldn't make it a rubble pile. And then many of them are glued binaries. When you look at them, you can see, oh, this was one and that was one, and over the course of time, they've merged. And so you have a sort of an issue there that they could unmerge while you're doing the capture, and that would, as was said just recently. The other one would be don't leave a trail.
Okay.
Don't leave breadcrumbs across the...
Don't be a space polluter.
Yeah.
All right, very good.
Andre, I'd respectfully request that you rephrase that last bullet.
Certainly.
I think in our assessment of deployable structures, we found that they are actually lighter than inflatables. And so I would...
all right, that's one of the reasons why. This is one of the reasons why I wanted to put it out, because I anticipated I'd get some good feedback from some of the participants. All right.
Maybe we should say there's debate about that.
That's fine. That's a good point, James. Well, remember, this is an open discussion, so part of the reason of having a seed input is to stimulate discussion. So if you'll take it in that spirit,
that's fine.
I appreciate it. Yes, sir.
Sort of along the lines of what the previous, for this gentleman's comment was, I think it's important when people analyze these capture mechanisms that they don't just think about, what's happening with that mechanism itself, but what forces and stresses and strains they're actually placing on the object that they're grappling with. Because since we don't understand the strength and the surface morphology, et cetera, of these boulders and the like, some of these activities may actually, put a lot of stress, a lot of pressure on that body that could disaggregate it or wipe, fine materials off the surface. Other approaches may actually treat it a little more gently. And that should probably be an important discriminator between the different types of approaches that you would ultimately develop.
And I would share with you, as Scott Bellman mentioned earlier, I participated and helped lead a team this summer in looking at analysis of alternatives for capture systems. And one of the concerns we had was where we're going to break up the rock, as we sought to capture envelopment. So we did identify that as a potential area for study.
Right, because you could run into environmental issues where if you rub a bunch of fine dust off the surface, that would then potentially contaminate some parts of the spacecraft, et cetera.
Right. So. Very good. Okay, next input. Yes.
Just one thing. Online there's been a discussion on the problems or the issues of bringing an asteroid and docking it to the ISS. I believe there's a misunderstanding, and it may be good to actually clarify what the goal is once we capture the asteroid as to what we would do with it.
So I would say at the policy level, which was, I think, covered well in the initial workshop, the goal is to, once we've captured the asteroid and returned it to the Earth-Moon system, is to send our astronaut team out to do some exploration, some sample collection, and then return those samples back to Earth for analysis. So one of the reasons that the policy and